it is very nice to see some familiar faces. My name is Fahad. I'm going to talk about the role of tropical easterly jet on the Bay of Bengal tropical cyclones. Along with me, there are other people that contributed to that project is listed in here. This talk is somewhat similar to what the previous talk, but I'm going to talk about Bay of Bengal tropical cyclones and tropical easterly jet. So Bay of Bengal Ocean Basin, located in North Indian Ocean, is known for deadly tropical cyclones. Specifically, if we look at the most deadliest tropical cyclones in the world in the right-hand side, out of 10, you will see that 8 are from Bay of Bengals. Other 2 are from West Pacific that hit Vietnam and China. So specifically, the Great Polar Cyclone that hit Bangladesh in 1970 was one of the deadliest tropical cyclones in history that killed nearly 500,000 people and created a humanitarian crisis at that time. The Bay of Bengal has substantial energy for cyclone formation due to high sea surface temperature, but at the same time, it is very hostile to cyclone development because of large vertical wind shear associated with the tropical easterly jet. So Bay of Bengal poses a recurrent threat to countries like India, Bangladesh, Myanmar, and Sri Lanka. So it is very important to understand how those tropical cyclones will be changed in the future climate. So general expectation is that the warmer sea surface temperature increase the frequency and intensity of tropical cyclones. A lot of studies have shown that in different ocean basins. However, previous modeling studies indicated that unlike any other basin, Bay of Bengal tropical cyclones is projected to decrease in the future climate, which is surprising. This study aims to understand the dynamical mechanism driving the changes in frequency and intensity of Bay of Bengal tropical cyclones under global warming conditions using high-resolution CMF6 models. The role of tropical easterly jet and vertical wind shear was previously overlooked for a couple of reasons, but most likely the tropical easterly jet was not simulated properly in CMF6 models because of the not having higher vertical resolutions. The study's goal is to establish the relationship between the tropical easterly jet and Bay of Bengal tropical cyclones in the current climate and use this information to examine the evolution of tropical cyclones in the future climate and to see how this tropical cyclone will be changed and if the mechanism still exists for the future climate. In the left-hand side, we have a observed Bay of Bengal tropical cyclones track based on IBTRAC's data from 1979 to 2021. The red dots and blue dots are showing the genesis location of the tropical cyclones. And the red dots are for northern Bay of Bengal tropical cyclones, or blue dots are for southern Bay of Bengal tropical cyclones. But if you look at the seasonal cycle on the right-hand side, we can see most of the tropical cyclones start from April, May, June. And there is another peak season is October, November, December. And these 2 seasons are separated by the peak monsoon season in July, August, September. But what if we divide this based on a genesis of the location, where red is the northern Bay of Bengal tropical cyclones and blue is the southern Bay of Bengal tropical cyclones. As you can see, northern Bay of Bengal tropical cyclone somewhat is more active, similarly, both from May, June, July, pre-monsoon and post-monsoon, whereas the southern Bay of Bengal tropical cyclones are mostly active in the October, November, December, whereas the pre-May, June, they're a little bit weaker. So if you look at the vertical profile, wind profile over the central Bay of Bengal, computed from MERA2 from 1981 to 2021, and the zonal wind shown as a red color and marginal wind shown as a blue color. I'd like to focus on the pre-monsoon season, April, May, June. On the upper troposphere, 100 to 200 hectopascal, specifically for zonal wind, where tropical easterly jet is. If you look at the April, May, June, so tropical easterly jet is negative in the sign, so more negative is more stronger. As you can see in April, May, June, they are somewhat positive even, close to 0, and tends to be strongly negative when we peaks toward the summer monsoon. When it comes to July, August, September, the tropical easterly jet maximum during summer monsoon season, which is 150 to 100 hectopascal. And even after that, October, November, December, it goes back to close to 0 and even positive, which means the tropical easterly jet weaker in that time. So if you look at the seasonality of the wind shear, which is calculated based on U150 minus U850, a lot of paper actually calculates it based on 200 hectopascal instead of 150, but I think that it is very important to take 150 as the peak of the tropical easterly jet is actually 150, not 200 hectopascal at the Bay of Bengal. So if you look at the wind shear, the top figure shows April, May, June, and U150 minus U850 basically shows there is a positive values over the land, which is related to the wind shear, strong wind shear related to the subtropical jet. Whereas in southern Bay of Bengal, it is negative and related to the tropical easterly jet, and there is a white strip of weak wind shear between positive and negative values over the April, May, June. I'd call it like -5 to 5 meter per second of weak wind shear strip. If you look at the July, August, September in the middle figure, it's almost all of the Bay of Bengal is taken over the negative wind shears. This is a very strong wind shear. There is no weak wind shear anywhere. And this is because the tropical steely jet is maximum in that time. And if we compute negative tropical steely jet minus low level monsoonal flow, we have a very negative, strong wind shear that suppresses all the tropical cyclones development. As a result, we don't have any tropical cyclone at that time, or very low numbers. If we go back to October, November, December, we again see that there is a weak wind shear exists again, minus 5 to 5 meters per second, where tropical cycle development are most likely to be, and the positive values kind of pushes to the southern Bengal from northern to southern, which is related to subtropical jet, and negative values are associated with tropical easterly jet. Now, if you look at the composite analysis based on what the tropical cyclones are, so red dots for northern Bay of Bengal and blue dots are southern Bay of Bengal, and if you look at the wind shear composite analysis based on the day of the tropical cyclone genesis, and the red dots, based on the red dots, if we have a wind shear, the top figure is that, and based on the blue dots or southern Bay of Bengal, we have a figure in the bottom. As you can see, when we have a Bay of Bengal tropical cyclone in the northern Bay of Bengal, the weaker wind shear strip kind of shifts to our northern part, but for the southern Bay of Bengal, it shifts to the southern part, which basically indicates that the tropical cyclone's genesis location is consistent with the weaker wind shear strip location. So wherever we have a weaker wind shear strip, the tropical cyclones tends to be generated in that region. So again, this is not based on any season specific, but just wherever the tropical cyclones is, we see that that's where the weaker wind shear tends to be. Now, based on that information, if you look at the future climate, so this is CMF6 12 high-res models, which have historical data from 1950 to 1979 and future data for 2020 to 2049. And the results are showing for April, May, June here. Here we see wind speed and sea level pressure, which is composite mean over the life cycles of the tropical cyclones, where increased wind speed and low sea level pressure are associated with the tropical cyclones. If you look at the future minor historical in the bottom panels, you can see in the future, wind speed tends to be decreased associated with the tropical cyclones, and sea level pressure tends to be increased, which both indicates that the tropical cyclones in the future climate in the Bay of Bengal is projected to decrease in strength. But if you look at the track density, which shows the frequency of tropical cyclones, and look at the bottom right panels, so the frequency of the tropical cyclone also projected to decrease. So at the same time, we have a frequency and intensity of the tropical cyclones projected to decrease in the pre-monsoon or April, May, June. We're looking at the same figure, but for October, November, December, or post-monsoon season, but it gets interesting. If you look at the bottom left panel, future minus historical, we see there is a decrease in the wind speed and increase in the wind speed in the southern Bay of Bengal, and northern Bay of Bengal there is an increase, where the sea level pressure increases on the southern part, and northern Bay of Bengal it actually decreases. And both kind of indicates that there is a shift in the intensity of tropical cyclones. It shifts from southern Bay of Bengal to northern Bay of Bengal. And if you look at the track density, it kind of indicates similarly that the tropical cyclones, number of tropical cyclones also projected to shift toward the northern Bay of Bengal, sort of northwest. But the intensity definitely kind of shift toward northern Bay of Bengal. So if you look at the reason behind it, the wind shear, so this is April, May, June. Left panel shows historical climatological mean, CMF6 mean from 12 CMF6 models. And the right-hand figure shows that the future minus historical as a difference as a shaded color, and the future mean are shown as a blue contour. As you can see, the future minus historical shows that the wind shear projected to increase in the northern Bay of Bengal. Specifically, it shifts the weaker wind shear strip towards south, and almost 2.5 degree shift of that weaker wind shear strip from northern to southern Bay of Bengal, which basically suppresses tropical cyclone development in the pre-monsoon season. However, if you look at the October, November, December, there is no, there is an increase, but it's not statistically significant increase in the wind shear, or the shift in the weak wind shear is not significant enough. So if wind shear is not changing in the post-monsoon season, significant of what is driving the tropical cyclones change in the future climate. So instead of looking at the mean state, we are trying to look at the short-term variability here, which I think is a very key component for both seasons. So for short-term variability, we look at the relaxation episode, which is calculated based on 48-hourly mean zonal wind speed difference between the time step and the previous time step. And based on all the grid points and the 48-hourly time mean, we create a PDF or probability distribution function for historical and future, where historical shown as the blue color and future shown as the orange color, but it's mostly brown because its upper left area are shown as a brown color. But if we want to understand how those tropical easterly jet relaxation episodes are related to the tropical cyclones, we have to look at the extreme part of the PDF. Whenever the tropical cyclones extremely drops, so that's when the tropical cyclone develops from a depression to tropical cyclones in any sort of time. So if you zoom into that specific extreme conditions, we see that the large relaxation in the future decreases almost 19%. So it's more stable. So tropical easterly jet is more stable in the future climate. As a result, it suppresses more tropical cyclones to be developed. As a result, we have less tropical cyclones and less intensified tropical cyclones, even though SST is more warmer. So this sort of explains the October, November, December. We found that it also explains April, May, June at the same time, not showing here. So in summary, the future climate, the frequency and intensity of Bay of Bengal tropical cyclones are projected to decrease during April, May, June, despite warmer sea surface temperature. During post-monsoon, the tropical cyclones are projected to shift from southern to northern Bay of Bengal, and severe tropical cyclones are projected to increase, potentially impacting the coastal areas like Bangladesh, India, and Myanmar. So it is very important to understand how early warning system will be changed in the future climate and how we can implement this information for our early warning system. The mean state and short-term relaxation episode are very important for April, May, June, but for the future climate in October, November, December, is the short-term variability of the tropical easterly jet is more important. Finally, I leave our paper, which is published in the Journal of Climate recently. But if you have more questions, you can ask here or you can send me an email. Thank you.
So are there any questions? Okay, so if there is no question, maybe I can.
Go ahead.
Oh, is there a question? Okay.
I just have a comment. I mean, I will strongly suggest you enlarge your analysis domain because, well, the Bay of Bengal is very sensitive to a lot of external, like the monsoon to the west, the Indian monsoon and Southeast Asian monsoon, the Maritime continent, and even Tibetan Plateau. From the northern part of the Bay of Bengal and the southern part, there's a huge difference in climate features.
Especially I agree. For the so in Indian Ocean we have Arabian Sea and Bay of Bengal, but interestingly both of them are not responding similarly. In Arabian Sea, it is projected to increase in the tropical cyclones, but in the Bay of Bengal, actually decreases. So even though large scale circulation is very important for North Indian Ocean, they're not responding similarly for those. So we have to be very careful of what is responding to what. Even if we have a consistent change of the variable, doesn't necessarily mean it's influencing. So it's like correlation is not the causation sort of things. So I did actually look at, we did actually look into it, but it's a very interesting point. Thank you.
I have one question.
Okay. Sure.
I just wanted to know, did you consider like changes to like the Indian Ocean dipole in your study?
So the idea was to look at the projected climate change. So considering IOD and so PDO, obviously all of this has an impact in internal to decadal timescale sort of. But what if we have think about a world where we don't have those internal variability? If we want to look at the climate change impact of this, what will happen? So this is sort of looking at the mean state sort of change due to the warming conditions. And if we have a sea surface temperature, we don't necessarily see a difference. So it's not about like internal variability. IOD sort of has definitely impact. I'm not obviously expert on the internal variability part, more of the climate change perspective. But thank you for the question.
Okay.